Joining us right now is Dr. Glenn Fredrickson. Dr. Fredrickson, thanks for being with us.
Thank you.
And congratulations as well on having been named the 2017 MRS recipient of the Materials Theory Award. Your talk is titled Field-Theoretic Simulations from Advanced Materials to Quantum Liquids. So give us a preview of what you'll be talking about.
So basically, this is work about trying to develop new ways of doing simulations of soft materials. So these are things like polymers, complex fluids that are applied both in developing new types of plastics as well as consumer products. The typical approach to doing simulations of these types of materials involves using techniques like molecular dynamics simulations, basically classical mechanics descriptions of assemblies of particles. What we do instead is we convert those particle models into models involving continuous fields. And then we've developed numerical techniques for moving those fields around in a simulation box. And what that allows you to do is basically to access material structures that are much, much larger than you can do with the typical particle-based approaches, as well as equilibrate systems that would be not possible to be equilibrated otherwise.
So do you foresee this approach as being the wave of the future then?
I think for certain problems, certainly for collections of very large macromolecules, very dense systems, this is a much more efficient way to try to predict materials properties, material assembly.
What are some of the products or devices then that have resulted from the work that you're doing in this field?
So one particular area of application is in advanced lithography. So companies like Intel, Samsung, who are leading the next generation of microelectronic devices, both microprocessors and storage devices are struggling with the scaling limits of lithography, being able to pattern devices on ever smaller scales. So in recent years, they've become very interested in using self-assembling organic molecules like blockopolymers to spontaneously form patterns on about a 10 nanometer length scale that can then be transferred into silicon substrates. We've been using our modeling tools to anticipate how that self-assembly takes place in films and helping them design their processes. This is called directed self-assembly.
What then are some of the hurdles still to come with this?
Well, I think the hurdles there, the biggest hurdles are defectivity. This is an industry that doesn't like to tolerate defects. Usually parts per billion types of defect levels are really what you need. And soft materials that self-assemble are intrinsically defective. And the way you beat that is by directing them very strongly from the substrate and by sidewall features. We've actually spent a lot of time with our modeling tools trying to really understand defect concentrations and how you would run these processes in a way so you can minimize defect formation.
Final question on a fun note. You are a theorist, so how did a guy who's a theorist end up as Chief Technology Officer at Mitsubishi Chemical Holding Company?
Okay, great question.
I thought you'd say that.
Basically through about a 10-year relationship with Mitsubishi Chemical that started by running a research center at UC Santa Barbara, and then gradually developing relationships with chief technology officers of the company, one of which who became a chief executive officer, and invited me to go to Tokyo a few years ago to run their R&D enterprise.
Jumped at the opportunity.
I did.
The rest is history, as they say.
Indeed.
Dr. Fredrickson, thank you. And congratulations again. It was great to meet you.
Thank you very much.